Hi, everyone. Welcome to Astronomy on Tap. We're very happy to have you again for what is likely the very last, or maybe not, we'll see, depending on the second and third and 15th wave of COVID. Anyway, this is the last Astronomy on Tap before we take a break for... Hi, everyone. Welcome to Astronomy on Tap. And we're very happy to have you again, guest speaker, to conclude this session of Astronomy on Tap Talks. Before we start, let's hit 100 subscribers just to make me happy. This is my last Astronomy on Tap as a presenter, I think. So if you could just hit that subscribe button and we can go to 100. Also, I guess this will help us get some funding for next year or something. That would be great. So yeah, thank all of you who are watching. And I will now let Chiara introduce the speaker.
Hi, everyone. Yeah, welcome to this event of Astronomy on Tap. Our speaker today is Dr. Annagrazia Puglisi, also known as Anna, which is easier to pronounce. She's a postdoc at Durham University, and her research is focused in general on galaxy evolution, with a special interest on the extremes of the galaxy population in the universe. In particular, galaxies in the process of merging, which is what she will talk about today, and also galaxies forming stars at the highest rates. So Anna, welcome. In your career, you moved quite a lot so far. So you went from Italy to Germany, to France, and now the UK, which is something quite common, I would say, in our job, especially at the beginning. And this forces us somehow to keep the things that we carry with us at the very minimum level. Otherwise, the moves are going to be a nightmare. And of course, this is a problem, for people with a passion for Christmas and Christmas decorations in particular, like you. So you started this habit or tradition to buy little decorations, and particularly famous case among your friends is the one of the Christmas tree that you got in Paris, and that you left there with your office mates because you developed a very strong bond with the city and also with your friends, so they can somehow replace you, in the office. So do you want to tell us more about this Astro Christmas tree?
Well, I mean, first, yes, I mean, this whole passion for Christmas, I had it since a long time, but I think that Munich brought it up for real for me. Because, I mean, you can really feel the vibe of Christmas in the city. You have the Christmas market. So I started to really get into the Christmas thing. So then in Paris, it was my very first house, just by myself. So I decided I was going to buy a Christmas tree. But also, I mean, as you say, the problem is that you move a lot, but also that the housing in Paris is problematic and the houses are extremely tiny. So I had to get a really tiny Christmas tree. And well, his name is Erminio. And yes, it's very famous among my friends. So I think I can now show you Erminio. If I can share my screen. Let me see here. There we go. So can you see Erminio?
Yeah.
Yes.
Yes. So, well, at first it was in my home, but then I decided to bring it to the office. So to have an office a bit more festive. So, but eventually we got attached to it. So to him, actually, it's a male tree. So you see on the left, there is Erminio with his Christmas dress and all the lights and everything. And then some food, which was another peculiarity of that office, a lot of food, homemade and not. But then, I mean, we didn't want to take it down, so it stayed there. And so on the right, you can see the summer version of Erminio. Although you don't really need the sunglasses in Paris, but I mean, this is what we came up with. And so then, yes, as you're saying, I left it in Paris for my friends to enjoy. But then, I mean, I wanted a Christmas tree in my new town, home here in Durham. So I introduce you to his brother or cousin, I guess, which is Hermano. So the name is quite similar, but it's bigger because also the house is bigger. So yes, this is my collection of Christmas trees so far.
Nice. So the size is growing, you know, with the career path and age.
With the
cool.
with the
Very
age,
nice.
the
Thank you.
house.
So before we start the talk, so Ayush, you've been posting, and others have been posting on different social media, so you can follow us here. Oh, okay, I'm wrong here. Yeah, that's the mirror trap. So yeah, so if you followed us on social media, you maybe seen some questions, and we'll briefly recap the questions with Ayush now. And some answers are, and some answers are not in the talk. And we will discuss the answers at the end.
All right, let me share my screen. Yeah. All right, cool. Yeah, I was wondering, looking at those Christmas trees, what they would look like once they actually merge together.
It's in presenter mode, Ayush. We can see.
I'm sorry.
No.
You're spoiling.
You're spoiling the answers.
No. Then let's not give it the talk.
Is it fine now?
No, that's again presenter mode.
What is happening?
Well, just show it like that. I think it's fine.
Okay, let's show it like that. Okay, so the first question that we asked you all was, what is the name of this particular system of galaxies merging? So you have three options to choose from. Is it called the hook? Is it called the mice? Or is it called the shrimp? So please feel free to put your answers in the YouTube chat, or go to our social media and answer there. We will reveal these answers after the talk, and there may or may not be some hints about the correct answer in the talk, so pay attention. Now, the second question was more visual. Now, we're going to hear about galaxy mergers today. So we want you to identify with your knowledge which of these galaxies could be undergoing mergers. So we've got 6 options for you, very beautiful galaxies. First one is NGC 55. The second one is lovingly called the Tinkerbell. The third is NGC 1313. Number 4 is NGC 2442. Number 5 is ARP 261. And number 6 are the antenna galaxies. So try and memorize these images in your brain, remember the numbers, and tell us in the chat or on social media, which of these do you think are actually undergoing mergers? And finally, the third question is a yes and no question. So we asked you, when two galaxies collide or merge, do their stars that make up these galaxies, do they collide as well? So you have to tell us whether the answer is yes, the stars actually do smash together during the collision, or the answer is no, where the stars very nicely just pass through each other. So yeah, these are the 3 questions. Which of these galaxies are mergers? What is the name of this merger? And what happens to the stars when they go through? So yeah, keep the answers coming, and we'll reveal the answers at the end of the talk.
Great. And again, before we start the talk, so of course, news of the week is that you can actually see a comet in the sky now in the UK. So I'll just put in the chat a link to the Royal Astronomical Society. There is a nice diagram where and how you can see it. So you just need apparently a good pair of binoculars. Even you can spot it with the naked eye if you have good sky conditions. So it's quite exciting because you don't see them quite often. So it's called Comet Neowise after the telescope in which it was detected. Well, actually, telescope is WISE, but because they've shut it down and restarted it, it's now called Neowise. Anyway, so yeah, we'll start the talk immediately. And if you have questions, please start asking already in the chat, because we have a 20-second delay, so it helps when we can ask question afterwards. And of course, every question is welcome. There is no naive or wrong or stupid question. Often, it's the simplest question that are the most difficult to answer. So you're most welcome to ask anything about the amazing talk we will have from Anna. I think that's all. Anna, over to you.
Yeah, thank you, Romain. So now I'm going to share my screen. Share. Can you see it?
Yes, and it's not presenter mode, rehearsal. Anyway, okay. Yeah, great.
So I'm really very excited to be here with you and talk about this such a cool topic in astrophysics. So this is going to be my very first outreach talk, my very first talk on Zoom. So I'm excited and nervous, but I hope that by the end of the talk, I will be able to convey you some of the passion that I have for merging galaxies, and I will be able to convince you why these galaxies are important for our understanding of galaxy evolution. So I like to start with this image that is an image of the Hubble Deep Field. And this is a long exposure that has been taken with the Hubble Space Telescope of the same patch of sky over 6 months. What I like in this image is that there are a lot of galaxies here, as you can see. And those galaxies come in a variety of shapes, colors, and sizes. So I think that this picture is very nice because it gives you a glimpse of the variety of that we observe in the galaxy population. But despite there is a lot of variety, as you can guess from the image, we can still recognize some regularity, and we can classify galaxies in 2 main categories according to their shape. So first of all, we have spiral galaxies. They have their stars that are arranged into a disk, and as the name suggests, they also have some spiral arms. So I don't know if you can see my cursor here. Oops, can you see it?
Yes.
Okay, no, not again. Anyway.
Not the presenter.
No. Okay, but never mind. So what I wanted to point out here is that if you look at the image that I'm showing in the slide, there are some bits which have some blue and yellow, emits blue or yellow light. And those are actually young stars, so stars that have been formed quite recently. So this means that spiral galaxies on average are contain young stars. Another feature of spiral galaxies is that they contain large clouds of cold gas. This cold gas is mainly hydrogen, and this is the fuel for forming new stars. So we measure the capability of a galaxy to form new stars with what we call the star formation rate. And the star formation rate, to give you a sense of the Milky Way, which is a typical spiral galaxy, is of 2 solar masses per year, meaning that our galaxy is forming 2 new stars with a mass that is similar to the mass of our sun per year. Also, the other feature that I want to highlight here is that stars and gas move around in spiral galaxies in regular orbits. Then we have elliptical galaxies. Elliptical galaxies are round-shaped, although they can have various elongation. They sometimes are elongated a little bit like a rugby ball. As you can see from the image, the color of elliptical galaxies is quite different with respect to the color of spiral galaxies. And you see the light is more yellow-reddish. And this is because the stars that are contained in ellipticals are older, and they are being formed more than 10 billion years ago. And they also have more or less the same age. So they have been formed more or less at the same time. Those elliptical galaxies do not contain gas and do not host current star formation. Also, their stars are moving around or randomly oriented orbits. But this is not the end of the story. There are other galaxies that have an irregular shape. As you can see from the image here, which shows the antennae, again, in this kind of galaxies, you can recognize some some blue and white bits, and those are again young stars. In these galaxies, there is also a lot of cold gas, and there is cosmic dust. You can see the dust in the image as the brown parts. And the dust in particular is abundant in regions of intense star formation. And again, to give you an idea on how intense is the star formation, the system that I'm showing you here, the antenna, is forming stars at a rate of 22 solar masses per year, which is about 10 times more than the Milky Way. So we know with some details the properties of galaxies around us, but there are still some questions that we don't know the answer. We don't understand why galaxies come in such shapes, why some of them are ellipticals, why some of them are spirals. We don't know if there is a connection between these 2 classes of galaxies, and if there is, what is this connection? So a possible clue to answer to this question come from irregular galaxies. And in order to understand what was the role of irregular galaxies in galaxy evolution, Harton Arp, which was an astronomer from the US, collected nearby galaxies, nearby peculiar galaxies in its Atlas of Peculiar Galaxies. So this is a collection of about 340 nearby peculiar systems, which have been classified according to their visual shape. And in this atlas, we can find 5 main galaxy categories. We have peculiar spiral galaxies, where despite the peculiarities, you can still recognize the spiral shape. Then there are elliptical galaxies in which we can still recognize the shape of an elliptical. Then there are galaxies which look neither like spirals nor like ellipticals. And finally, we have group of galaxies and then galaxies that cannot be classified into none of the previous categories. So those galaxies are very nice to look at, but this is not the only thing that they have in common. The other thing that they have in common is that most of them comes in multiple systems. And this, for example, you may notice from the images that I'm showing you in this slide. Those are, I would say, quite famous examples from the Atlas of Peculiar Galaxies. We have, for example, HARP 273, which, as you can see, has this beautiful shape that reminds a rose. Then we have the mice, HARP 242, that gained its nickname because of these long streams of gas and stars that we can see in the image. And finally, we have, again, the antennae, HARP 244, which has this whirling nucleus. But then if you look at the wide field image, you can discover that this galaxy has extremely elongated tails, which gave them the nickname, the antennae. So those galaxies have in common the fact that they're coming in pairs, and they are actually involved in what we say it's a merger. And we call a merger the phenomenon for which two galaxies collide with one another because of the interaction between their gravitational field. And now in the rest of my talk, I'm going to walk you through the process of the merger to discover some of the effects that the merger can have on the two galaxies that are colliding. But before doing this, I think it's important to have a sense of the scales that are involved. So in galaxy evolution, we measure the distances in kiloparsecs. Now, I'm not going to explain you what a kiloparsec is, but what is important here is that the Milky Way, which you can see here in the image, has a radius of 15 kiloparsecs, so a diameter of 30 kiloparsecs. And you may also want to know that we live in the Milky Way disk with our sun, and we lie at 8 kiloparsecs from the center. Understanding the scales is important to understand also why we see galaxies colliding. So, I told you how big the Milky Way is. Now we can think to our closest large galaxy, which is the Andromeda galaxy. So in this image, which is not a real image for now, you can see that the Milky Way and Andromeda are separated by 780 kiloparsecs. And this is more or less 26 times the Milky Way size. So this means that galaxies are not very far away from each other, and also they are quite big. So this tells us that galaxies can get close to each other and they can eventually collide. So now let's go to the actual merger process. So to show you what happens when two galaxies collide, I'm going to first show you a movie, which is from a simulation. So in this simulation, we have two isolated spiral galaxies. As you can see from the image, they are nicely looking. They have, and you're looking at here at the stars that are contained in those spiral galaxies. They are separated by about, I would say, 5 Milky Way radii. And if you can see in the image here, there are some blue parts, which are telling us again that there are stars that are being formed while the galaxies are far away. So now I'm going to press play, and you see the galaxies that are getting close. They pass each other, And they start this sort of cosmic dance, which I think is quite beautiful to look at. And you see they get far away again, but then eventually they will start to get close again. And while they do this dance, I think you may see that their shape starts to be progressively distorted. And you see now they're getting closer and closer until the end, where we can no longer recognize two separate systems. So we ended up with a single galaxy. Now let's go and break down this process a little bit into pieces. And let's do this with using this graph. So this graph is showing you the orbital evolution of two galaxies during the merger. Comes from another simulation of two spiral galaxies colliding. And you see in the y-axis, we have the distance, which is again measured in kiloparsecs. And on the x-axis, there is the time. And the time you see in this case goes from 0 to 600 million years. And this is about 13% of the age of our sun, which is 4.6 billion years. So in this case, in this specific case, the merger lasts 600 million years, but the actual duration of a merger depends on the initial conditions of the orbits of the two galaxies. And also, I would say that this is a relatively long process for galaxy evolution processes. So as I said before, we start with two isolated disks. Now the image that you're looking at is a snapshot from the simulation from which the measurements are being taken. And then you see the distance reduces, and it reaches a local minimum point, which is what we call the first pericenter. And you can think about this point as the moment at which the proper interaction starts. So you see in the image here that the shape of the two galaxies interacting is starting to be altered. And in particular, you see there is a sort of bridge between the two nuclei. Then the galaxies pass each other and they go far away from each other. So the distance between them increases again. And you see that, again, the stream of stars between the two nuclei. And also you may notice these elongated beats, which are what we call tidal tails. And those are similar to the tails that we saw already in the antenna or in the mice. Then the galaxies move again, get close again, until this point, which we call coalescence. And this is the moment when we can no longer recognize two separate systems, and it's also the moment in which the merger ends. So one thing that we can learn from this sequence of images is that the merger has an important effect on the shape of the galaxies. And as it is able to deeply alter the shape of the galaxies that are involved in the merger. So this is one of the reasons why we think that mergers are important, but this is not the only one. So the reason the merger has another important effect on the gas that is contained in the galaxies. So I'm going to show you what is the effect of the merger on the gas with another movie. In this case, we are no longer looking at the stars, but we are looking at the gas which is contained in the galaxies. And in particular, the yellow color here indicates the most dense gas, which is the gas that is going to form stars. So at first, the simulation in the simulation, we look at the isolated disk of a galaxy from the top, but eventually, now we see that the two galaxies colliding again. I think you can notice already that the shape of the gas is deeply altered, much more than what we were seeing before with the movie showing the stars. And also, you may notice that there is a lot of yellow in the center of the two galaxies. And also, by the end, we see that there is a large concentration of yellow in the center of the single system. So what is happening here? So during the merger, the large clouds of gas that are contained in the two galaxies collide because they are large. And because of this collision, they lose part of their rotating energy. So they sink into the center of the galaxy and they accumulate there. So during the merger, what happens is that there is a large accumulation of gas in the nuclear part of the galaxy. Because of these very high densities, then the gas is being converted very efficiently into newly formed stars. So, this means that the star formation rate of the galaxies involved in the merger is going to be affected by the interaction. And indeed, you can see this from this graph, which this time shows the star formation rate as a function of time. So in this graph, you can see the evolution of the star formation rate during the merger. As I said before, the merger has an effect on the star formation rate, and you can see that the star formation rate goes up and down as long as the merger evolves. In particular, at the coalescence, you may notice that there is a strong peak. And this is indeed an important phase of the merger. This is what we call the starburst phase. And this is a phase of extremely intense star formation. And here, for example, in this specific case of the simulation, the star formation rate of the merging galaxy goes up to 50 solar masses per year, which is extremely high. And because it is so high, the star formation rate, the gas gets consumed quite quickly. And indeed, as you can see, the starburst phase has an extremely short duration. In this case, for example, it has a duration of 50 million years, which is about less than 1/10 the whole merger duration. So this is a quite rare phenomenon. But the question now is, do we observe this starburst in the real universe? And the answer is yes. You can see here one of the most, the prototypical examples of a starburst galaxy. And this is the nearby galaxy ARP 220. This galaxy is a late stage merger at the coalescence phase and is also a starburst. You see in the image on the left that there is a lot of blue and white light here. And this is the up to 120 nucleus. And the blue light here is the light from the star clusters that have been formed during the interaction. But to actually look at the starburst, we need to look at the image on the right, which is a zoom in the ARP 220 nucleus. So the starburst is actually confined in this region that is emitting red light. And this region is so tiny that it's like 1% of the size of the Milky Way. But despite it is so small, it is contained a huge amount of gas. The gas that is contained here is about 3-4 times the gas of the Milky Way. And indeed, this galaxy is forming stars at a crazy rate. The star formation rate of ARP 220 is of about 100 solar masses per year. So this means that this galaxy is forming stars at a rate which is 50 times faster than the rate of our Milky Way. So this tells us also that the gas is going to be consumed quite quickly in few million years. So now we are about at the end of our journey through a merger. So as I said, we started with two nicely looking isolated disks. We went through a bumpy ride. We had some bridges, some tails, a bursty phase, and now we are left with what we say is a merger remnant. So now, to finish, I want to focus a little bit on the actual properties of this remnant. So the remnant is now dead, meaning that it's no longer forming stars, and this is because most of the gas has been consumed during the starburst phase. So because most of the gas has been driven into the center and a lot of stars have been formed into the center, this remnant has a large amount of stars located there. Also, the stars have been formed nearly at the same time during the burst. And finally, the merger scrambled the orbits of the pre-existent stars. So this means that the remnant now has a roundish spheroidal shape. So I hope that these features of the remnants remind you of the features of elliptical galaxies. And indeed, this is also the other reason why we think that mergers are an important process in galaxy evolution, because mergers are the best candidates to produce an elliptical galaxy. So to conclude, we think that mergers are important because they can alter the morphology of a galaxy. They can affect the star formation rate of a galaxy, and they can boost it up. And they can also produce ellipticals. And so to end, I want to show you another movie, I think my favorite one, because this is the movie that simulates the process that gave us the beautiful image of the antenna that I showed at the beginning of my talk. And thank you.
Thank you, Anna, for this amazing talk. Thank you very much. So please start asking questions in the YouTube chat, and we will ask them to Anna. In the meantime, let's go over the questions that we asked on social media. Over to you, Ayush.
Thank you, Roman. I'm not going to attempt to go full screen this time because I mean, although there's no point of spoilers now because they will be spoiled. Okay, so just a quick recap of all the questions that we've been asking you the past couple of days. First question is, what is the name of this galaxy merger? I think there were some clues in Anna's talk, so if you've been paying attention, then now's the time to quickly type them in, and then we'll see if you got them right. Question 2 was about which of these galaxies are undergoing mergers. Now, I think we saw a lot of these images in Anna's talk. So if you were again paying attention, then you should be able to now be an expert in identifying merging galaxies. So just have a look at these 6 beautiful images and tell us which ones are mergers. And finally, we asked you, when 2 galaxies collide, do their stars collide as well? So just tell us if the answer is yes or no. So should we move on to the answers now, Roman? Is that?
Yeah. I think we can.
Right. So drum roll, please. The name of this galaxy merger is the Mice. Anna, why is it called the Mice? We've been thinking about what about this galaxy looks like a mouse or mice. Do you know? Or
it's because of the streams, the tails actually that you see. And how to know how to call that in English, but it's like the thingy of the mouse that reminds that. I mean, yeah, it's not obvious the name, but
maybe I can see it, but I mean,
they are very long, very tiny.
I have to be honest, I was fully going for the hook, and so yeah, I'm quite.
It looks like a hook. I mean. Yeah, but yeah, I mean, astronomers cannot be trusted to come up with.
I honestly would go. I mean, I would think about that, but I would think about a cat more than
exactly.
A mouse. But
I agree. So,
okay, they are pretty.
Exactly. So, I think it was maybe like to get some positive PR for mice because they really have a bad reputation. So
yeah, maybe.
Yeah. Anyway. All right. So the answers to merging or not merging are now on the screen. So NGC 55 is not a merger. Even though it is elongated and it has a weird shape, but it is not 2 merging galaxies. Tinkerbell obviously is a merger. Anna, how many galaxies are actually merging in here?
So I think there are 2, but I think there might be even more than 2. The answer is not obvious because sometimes it's not easy to identify various components. Those systems are extremely complex. There is a lot of going on there, so it's not straightforward. I think there should be 3, but I'm not 100% sure.
Well, I guess this just goes to show how difficult it is to characterize these complicated systems.
So maybe just the trick on the first one. So it's elongated because it's an edge-on spiral. So you have this, you have this idea of the face-on one that you have on your desktop, laptop background maybe, but that's an edge-on, so that's why it's so elongated. So that was the trick.
Yeah.
Okay. Number 3, NGC 1313 is also not a merger, although it is an irregular type galaxy. So, which is very interesting sort of morphology in its own. But as far as we know, it it is not a merger.
Yeah.
Number 4.
Not all of the irregulars are mergers. A
Yes.
lot of them, but not all of them.
Right. The mysteries of the universe. Okay, number 4, NGC 2442. It is not a merger. However, there is a little catch here. We think, or astronomers think, that there is a galaxy that passed by the galaxy in the middle that led to its weird deformation and the shape that it is today. So yeah, I don't know if any of the panelists want to add something to this, but it's also very interesting how just close encounters can change the shapes of galaxies as well. So you don't have to actually collide.
Yeah, I mean, sometimes also the galaxies can pass close to each other, but maybe they are moving, their relative velocities are too fast, so they do not collide effectively. But the fact that they pass close to each other can affect the shape anyway. So you have this sort of distortion, some elongation, some asymmetry that creates, as for example in this case.
Yeah. So yeah, lots of funky things happening when galaxies pass near each other.
For this galaxy, one of the hypotheses is that the kind of companion is also a kind of a smaller galaxy is more difficult to identify. So that's also why it's even difficult, to identify the galaxies in close encounters or mergers.
Well, this is interesting, Chiara, because it also points out to the fact that, I mean, there are different things that happen depending on the kind of mergers that we have. The process that I've been talking about is what we say it's a major merger, which means that it's a merger between two galaxies that have more or less the same mass. But when the two masses are quite different, then there are different things that happen, as this case, for example.
So it may be possible that the merging galaxy is so small that it's very hard to identify on its own, but you can see its effect based on the changes in the shape.
Yeah.
Cool. All right. Moving on. Number 5, ARP261. This is a merger, and I think we can see the two galaxies sort of after the merging phase. Do you think this is before merging or after merging? What phase?
Well, if you still can see the two galaxies, then it's like in the process of colliding.
Right. So it's just had its, or it's about to have its near.
Yeah, usually, I mean, at the coalescence is the moment when you stop to see big alteration in the shape.
Okay. Very cool, very cool. And then finally, the antenna galaxies are also a merger. Do we have any fun facts about this?
Well, I don't know. I think those are my favorite merger to start with, as you might have guessed, because I showed it many times. And to me, what is mesmerizing about these galaxies is that this is the same galaxy as the big image that you saw in the beginning of my talk. So they look totally different, but this is just a zoom in. And also, I think it's interesting to point at the size. So this thing, the nucleus is about 4 kiloparsecs per 4 kiloparsecs, I think. But then the actual tails are extremely elongated. I think they are more than 100 kiloparsecs.
So that gives it a very spectacular sort of morphology. And I was also impressed by how accurately the simulations were able to reproduce what we see.
Well, this is a well-studied system. It's one of the closest irregular merger galaxies that we have. So theorists have been trying to study them in quite a few details by now.
So they're doing a great job. So. All right, so these were the answers for mergers and not mergers. I hope you had a few of them correct, and if you got all of them correct, congratulations. And then finally, when two galaxies collide, their stars do not collide with each other. They simply pass through each other as if there's nothing around them. And surprisingly, on Twitter, everyone got this answer correct, so well done. Anna, why do they not collide with each other?
Everyone knows now already.
Everyone knows, but
Yeah.
there's something extra.
So no, the reason is that stars are extremely tiny, and also they are separated by a large amount of space. There is a lot of empty space between stars. So, like for example, if you think the closest stars to our sun is Proxima Centauri, and if you compare the diameter of the sun to the distance between the sun and Proxima Centauri, you have a difference, a ratio of 8 order of magnitudes, which is a lot. It means that the chance of these two stars getting close is basically 0. Whereas, as I said, galaxies are big and they live close to each other, so they can collide. And also the clouds of gas are much bigger than the stars. So they can collide when two galaxies cross each other.
Right. So even though there's a lot of gravitational effect, the chances of each stars colliding is very
because you need to get very close for them to feel, to collide. Then there are effects on the stars. It's not true that they do nothing, because the merger perturbs the orbit a little bit. Eventually they might get kicked out from the galaxy, or they can go in, they can change their orbits, they can get some elongation, but they do not collide.
Yeah, very cool.
So I have an answer on the chat that says, yeah, they do collide, but not very often. And
not during.
If you
it's
say
very unlikely.
Not very, 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 very often, then it's a full point, I guess.
Well, yeah, that's true. Well, it's a big universe, old universe.
So yeah,
statistically, yeah, it's not.
Statistically, it's no.
All right, so these were the questions and the answers to those questions. Thanks for participating, and well done if you got many of them right. Over to you.
Cool. So let's go to the questions. So I see we have questions. Oh, by the way, yeah. So if it's the first time you land on this YouTube page, we have a lot of talks, and you can just go and look. We had about 9 or 10-ish, so there is plenty. And then if you go to our channel page, we have like brothers and sisters in all the world that are doing AoT in every single city, and they all go now to YouTube. So you have like, I don't know, perhaps hundreds of talks. So that should keep you busy for some time. Okay, questions. Maybe Chiara, if you want.
Yes. So we have a question from the chat. If stars can end up doing random motion within globular structures, so intersecting the planes of their orbits, can the same be said about planetary systems?
Well, that's an interesting question. I never thought about that, honestly. But so the question is whether the planetary system orbits can get perturbed during the merger?
I guess so.
I think so, yeah.
Looks more global.
Maybe. I don't see why not. Yeah. Maybe yes.
But, yeah, maybe the planetary systems are so low mass, I guess they don't feel that much of an impact. I don't know, just...
Well, the stars are going to be affected by the interaction in their orbits. So if the central star feels something from the merger, then I would say that yes, even the planetary system around is going to be affected. I don't know whether it's interesting for this question specifically, but for example, well, no, I'm going to spoil something else. Okay. So I would say yes.
But it's very, very rare because we have these pictures from ALMA where you can see all the planets forming in the disk, so like in the protoplanetary disk. So they start up into a plane, and so you would really need a violent merger, I guess, to perturb all of this.
Oh, maybe I didn't understand the question. I thought it was during the merger of two galaxies.
Yeah, or even after. I think the question is more general. Can you have a system where you just have planets going in all different random orbits, right?
Well, I think it's also I mean, I really don't know, because also when we study galaxies as a whole, we don't go to such small scales. It is very hard to simulate the different scales. The planets are very much on short scales, whereas a galaxy is extremely big. So I don't think this kind of simulations go into the detail, but it's definitely interesting. So I will look it up.
Yeah, it's interesting. Yeah, we're not. I'm sorry, we don't have exoplanet experts on board. I think my last thought is that because of the methods we use to detect exoplanets. So, for example, the transit method, when you need the planet to pass in front of the star, I guess we can only detect systems that are pretty much aligned. I don't know for the radial velocity, but I guess we're biased to align systems in a sense.
I know better than me.
Anyway, well, yeah, we have other talks on exoplanets. Next question.
Yeah, so the next question is, what is the frequency of merging galaxies in the universe?
So that's a very interesting question, actually, because it's a matter of debate. So there is, let me see, maybe I can show you something. So let me see if I can share the screen again. So can you see the screen?
Yeah.
Okay. So, well, here you have, I'm going to explain the plot. So you have on the Y the percentage of starbursts, and on the X the what we call the redshift, which you can think as more or less the age of our universe. So we are at 0 point, age of 14 billion years, and then when the redshift increases, the age of the universe decreases. So you look at the universe, which is younger. So you see, so to answer to the question, maybe you can look at this curve here, the purple one. So you see this is the percentage of mergers according to simulation. You see it's quite small in the local universe. It's about 2% of the galaxy population, but then it increases with the redshift. So in the younger universe, we think from simulation that the mergers were more frequent. Then another interesting piece of information here maybe is also that there is some tension between what the simulations tell us and what we do observe, because here you can look at the points here, the one in black, for example, and this is the percentage of starburst. So not exactly mergers, but more or less mergers. And you see this, the curve from the simulations goes up, whereas the observations stay more or less flat, and they stay around, that's the 3% of galaxies that are in a starburst phase. So mergers in general are from the observations, they are not extremely common to observe, and they are about in the starbursts are like the 5% of the galaxy population.
So it is a very open question, and
well, there are some answers of why we have some tension between the simulations and the observations, and part of that comes to the fact that it is really difficult to identify observationally the mergers. And also the observations are biased to some phases of the merger, depending on the technique that you use to identify the mergers. So it's really hard from the observations to get a complete picture of the number of merging galaxies. So by correcting some of the effects, I think the tension between simulations and the observations was reduced. But the bottom line here is that they are rare percentage of the galaxy population, although during the life of a galaxy, they can occur and they have important effects on it.
So perhaps an interesting number for our viewers is like in a galaxy like the Milky Way in which we live, how many mergers did it have, during its lifetime of 14 billion years?
Well, that's, I don't know specifically the number of mergers that it had, but I think it had, well, there was a major collision. No, I don't know. I don't want to say something wrong, but there was a major collision in the recent past. But the interesting thing maybe is also that the Milky Way is going to have a merger relatively soon with Andromeda. And well, let me grab the slide where I have some information about that. So in about 6 billion years, the Milky Way and Andromeda are going to collide.
Relatively soon, for an astronomer.
Yes, exactly. And well, the image below is that of course, is sort of an artistic impression. As you see here, there is the arm of the Milky Way, and then there is Andromeda at the point at which they reach the first pericenter.
Yeah, if any of us is still around after 6 billion years, it's going to be
Sorry?
very nice. If any one of us is still around after 6 billion years, the sky would look really
very
spectacular.
interesting. Yeah.
Yes, well, I think that's all. Thank you very much, Anna.
Thank you.
If you can, stop sharing your screen. So yes, this is the end of this talk, and this is also the end of a series of Astronomy on Tap. I will personally say bye-bye because I'm moving to Germany after this, so I won't be hosting anymore. But I'm sure Chiara and Ayush and Corentin will you're in safe hands.
Roman,
I think
if I can quickly ask you, how was your experience hosting Astronomy on Tap?
Hosting astronomy, it's great. You should absolutely do it. That's it. You're the next. Yeah, I can. No, I think. I cannot give you the video. I cannot even send you the passwords to the account because you have it. So it's same for you, Chiara. I mean, there's nothing to do really. I think it's been great hosting Astronomy on Tap. We've seen so many great talks. We've reached out to many people. I have to say my only regret is we didn't have enough minorities and Black astronomers, and perhaps women. Maybe we should have more, but I mean, you have to consider the ratio already in the field. But yeah, we should have pushed more, but the problem was lockdown, I think, and it was already very difficult to get the speakers. So we could showcase the work of people that had some time, and others had family issues and childcare issues, and it's totally fine that they don't have the time right now. So also yes, with the return to normal, I hope we'll have more people and we can push the voice of minorities in the field. That would be great.
Well, you're moving to Germany now, which means you can come back as a guest speaker.
As a guest speaker.
Well,
but in regards to what I've you've seen my white face already too many times, so please show someone else. I think we have the luck that here in London we have a lot of astronomers, so we can continue. So that's one thing for sure. Yeah, I think the viewers can expect that we will have a lot of speakers, and I think we had mainly speakers from UCL, and I think we need to have more speakers from other institutes, and
I think the big step would be having it in actual pubs, because
that's the elephant in the room, right? That's the elephant in the pub.
Visit us, and it'll be nice.
So one of the goals for the next season will be to collaborate more with the astronomers from other universities. So if you are watching us and you are from university in London, please let us know if you want to give a talk or participate in the organizing committee. Yeah, and I wanted to say a big thank you to Roman, because I think he did a great job in sharing all these events, and it was a lot of fun to work with you for Astronomy on Tap. And yeah, remember not to buy a big Christmas tree before going to, to Germany, and buy a small one in case.
But remember to enjoy Christmas in Germany.
Yes, yes. No, that was the first thing I wanted to do when the DIY shops open again. Buy a Christmas tree.
Okay.
Just go to a forest and chop one,
Oh, no,
go to the Black Forest.
Imagine going out on the Eurostar with the tree on my back.
As you do.
Send a picture.
Right. Okay. Thank you, everyone. So this is the end of the, let's say, season 1. Let's call it season 1 of Astronomy on Tap London. Season 2 will be somewhere, sometime. We'll keep you updated. Actually, if you follow us on if you follow us on social media or you subscribe to the channel, we'll make sure to post these online. And I think even though it will be in pubs, we will try to keep them posted up on YouTube for people that cannot travel or come or don't have the time. Yeah, we hope you enjoyed it. And also, if you know astronomers, you can also suggest them to come. That would be great. And yeah, we still haven't hit 100 subscribers. I'm
one more. Come on, let's give Roman a parting gift.
I will stay on the live until there is 100 subscribers.
Not end the stream.
Yeah, and final words. Big thank you to UCL, who gave us a bit of money to run this pro paid Zoom account. It's not much, but that's the small help that we needed to start this. So thank you very much. Okay, bye.
Bye.
See you soon. Thanks, Anna.
Thank you.
Thanks,
Bye.
okay.